Hi everyone, we're solving this chemistry paper today. This is 9701 paper 42, May June 2023. So before we begin, let's take a look at the threshold. This is it for this variant. As you can see, for paper 42, out of a maximum available 100 marks, A was at 60, B was at 47, C was at 38, D was at 28, and E was at 18. Right, so let's write that down. I'm solving chemistry paper for after a long time because it usually takes a lot of effort. However, the reach isn't that great, so yeah, if you do like the content, please consider subscribing to the channel, hit the like button, and share the video with your friends. So out of 100, A was at 60, B was at 47, C was at 38, D was at 28, and E was at 18. All the variants had more or less the same difficulty. It seems like this paper 42, was a bit harder than the other ones though, comparatively. As you can see the comparison. Okay. Also guys, if you do like all the question paper solving, and if you want access to all of these, of all my solved papers for 2023, 22, 1, 20 till 2016, I have most of them done, including paper 5 for physics, chemistry, bio, as well as P1, P3, Pure Math 3, Statistics S1 and M1. You can consider supporting me on Patreon. It's patreon.com/CAI paper solved, where there are 3 tiers. The first tier is for general support regarding question papers and exams. And in the second tier, you get access to the notes and paper solving requests. You get access to ad-free videos as well. And in the last one, you get access to all the notes for physics and chemistry for every topic, as well as the solved papers for all years, including one-on-one video meetings with me once or twice a month, where we can solve your problems individually. So yeah, you can consider supporting me here for the ultimate learning experience. Anyway, without further ado, let's begin. Question number 1. All right. So what do we have here? Group 2 carbonates decompose when heated to form the metal oxide and carbon dioxide. Suggest a mechanism for the decomposition of the carbonate ion by adding 2 curly arrows in this diagram. Fine. So we know that it's going to turn into an oxide ion, and we're going to end up with carbon dioxide. So we need this CO2. This is what we need overall. Now, how are we going to do this? Basically, think about it. This oxygen over here already has an excess electron. So this oxygen does as well. So basically, since they highlighted this lone pair, they actually is implied that they want us to, show this arrow from the lone pair to the bond over there. So it turns into carbon dioxide, right? But this carbon over here can't have 5 bonds. So, and yeah, it can't have 5 bonds. So we need to get rid of this bond. So this curly arrow, there's going to be heterolytic fission of this particular bond over here, and it's going to turn into the O2 minus ion. Okay. So this is basically the mechanism. They drew the arrow from here, but it's the same thing. Okay. So one arrow is going from the O minus to, and in fact you could draw it the other way around. That's totally fine. Okay. But since they've already highlighted a lone pair, they probably want you to, transfer this electron to the carbon over there. All right. So that's probably the logic. So describe the variation in the thermal stability of group 2 carbonates. Okay. So we know that the thermal stability, what does it do? Increases, right? The thermal stability increases down the group. So what is the logic behind this? We know that down the group, the cationic radius or the ion size increases, right? We know that down the group, cationic size or ionic, sorry, they actually said cationic radius is the same thing, but it's better if you write cationic radius, or down the group ion size increases. Fine. And what else? Or you could say that the charge density of the cation, or you could say that the charge density, same point by the way, charge density of the cation decreases, right? So ultimately there is less polarization of the anion, or less distortion. There's less distortion of the anion or the carbon ion, right? Fine. These are the 3 points. Thermal stability increases down the group because the cationic radius actually increases down the group, and ultimately due to this there is less polarization of the anion cloud, so there is less covalent characteristics, right? But more ionic character remains. Now what is the lattice enthalpy? It is the energy released when 1 mole of an when 1 mole of an ionic solid is the energy released when 1 mole of an ionic solid or ionic compound is formed from its constituent gaseous ions, okay, under standard conditions, but they particularly write from its gas phase ions or gaseous ions under standard conditions. So these are questions that we all know the answers to because these are extremely common, so you should get them right. This is going to appear in your October-November exam, by the way. It's on the 20th or something, I think, 20th October. Let me check. Yeah, it's on 27th October actually. You have a lot of time. So I am planning to release the other paper 4 variant, paper 4.1, by then. So keep an eye on the channel, hit the subscribe button, and smash the like button as well. Now, the lattice energy of the group 2 carbonates, the lattice energy becomes less exothermic down the group. The lattice energy of group 2 oxides also becomes less exothermic down the group. Fine. Del H lat of the carbonate and del H lat of MO change by different amounts going down the group. Both of them become less exothermic, but the amount differs. Suggest how the standard enthalpy change of decomposition reaction for group 2 carbonates changes down the group. Explain your reasoning in terms of the relative sizes of the anions and the relative changes in lattice energy down the group. By the way, guys, we do not have access to the data booklet, so we cannot take a look at that, okay? We just have access to the periodic table, as well as, you know, some common values that we need. So let's try to figure this out. This is a new question that we haven't seen before. First time that we're seeing this. So let's try to figure that out. Okay, so let's focus, since this is the first time that we got this, but it is almost, it's like a similar answer to the one for solubility of hydroxides and sulfates. It follows a similar trend. Okay, so let's write down the answer first, then I'll explain all the points, okay? So firstly, del H decomposition becomes more positive or less negative down the group. That is one marking point. Another one is why? Mainly because as you go down the group, what's happening? Why is lattice enthalpy becoming less exothermic. The charge remains the same, right? But the cationic size actually decreases. So the cationic size actually increases down the group, my bad, for the cation, and as a result, or the charge density decreases. So since the size increases, the distance between the cation and the anion has increased, so there is less attraction, right? So let's write this down, that the size or ionic radii. But here, what do we have to compare? What is the question here? Like they said that the lattice enthalpy of both of them become less exothermic. It's just that they change by different amounts. One changes more while the other changes less. Now suggest how the enthalpy change, standard enthalpy change of decomposition for group 2 carbonates changes down the group. Okay, so we're talking about decomposition. I'm going to draw a Hess cycle soon and explain your reasoning in terms of the relative sizes of the anions and the relative changes in lattice energy down the group. Okay, so let's write the answer first, then I'll do the explaining. The size or the ionic radii of the oxide ion is actually smaller than the carbonate ion. Okay, we'll see why this has an impact. So we can state that, so del H lat of oxides becomes less exothermic faster, or you could say less negative faster, or you could say changes more or changes faster. Just like the answer for solubility, yeah, one just changes more than the other. So let's try to figure this out using a Hess cycle, then I'll explain the reasoning again. So what do we know? What is the main reaction? Maybe we have a metal oxide, which is or a metal carbonate. We know that it decomposes to form the metal oxide as well as some carbon dioxide gas. Okay, now this is the enthalpy change that we need to find. This is the del H of uh, decomposition. Now hear me out. Here's the thing, we also have another lattice enthalpy, which is M2 plus the constituent gases and CO3 2 minus. It is gonna form this on that end, and we also have M2 plus you know an oxide ion, which is going to form plus carbon dioxide as well on this side, which is going to form this. Fine. So this is what we have for now. Now here's the thing, the lattice enthalpies fall as we go down the group. That is already mentioned in the question. We know why, because essentially the size of the cation increases, so there is increased distance between cation and anion, and so the attraction becomes weaker. Okay, so let's try to explain this in terms of this. All right, so here's the thing, the lattice enthalpies don't fall at the same rate. One just falls faster, mainly due to the size. Just think about the carbonate anion. It has 3 oxides as well as 1 carbon, while the oxide ion only has 1 oxide. As a result, just think about it, the oxide must be smaller than the carbonate ion. So it can attract the cation more strongly compared to this. But since the carbonate is bigger, the attraction for the cation will be lower. So this can be written as del H lattice enthalpy for the carbonate, and this can be written as del H lattice enthalpy for the metal oxide. So honestly speaking, like this Hess cycle is a rather unique one because we usually start from a common point, but we can turn it into a common Hess cycle like this. What if, I just draw an arrow like this? Maybe what if I just draw an arrow like this and I can just call this del H, and it's just a constant value, for example. So let's try to, connect the arrows. What are the roots? One root is this one, the other root is this. Okay, so can I just write them down? Can I write this del H value, which is constant, plus del H lattice enthalpy of oxide is equal to del H lattice enthalpy of the carbonate plus del H decomp. This is our Hess cycle ultimately. Now what do we need to find? We actually need to find the del H decomposition. So if I make del H decomposition constant, what do I end up with? Del H decomposition is equal to del H lattice enthalpy of the oxide minus del H lattice enthalpy of the carbonate plus del H constant, which we can ignore, honestly, which we can ignore. Now here's the thing, we know that any decomposition, right? Any decomposition enthalpy is already endothermic. This is an endothermic value. But suggest how the standard enthalpy change of decomposition for group 2 carbonates changes down the group firstly, and also explain your reasoning in terms of the relative sizes of the anions and the relative changes in lattice energy down the group. So both of them do become more endothermic. So what is the reasoning behind this? Okay, so as you can see, the value for enthalpy change of decomposition is lattice enthalpy of oxide, magnesium oxide, minus lattice enthalpy of magnesium carbonate. So hear me out. So the value of lattice enthalpy of magnesium oxide must be, it must be more positive. Okay, it must be more positive than this. Do we have any values over here? And clearly there is another logic. As you go down the group, since the thermal stability increases, right? So we need more energy to break down the bond, right? As you go down the group, you need more energy to break the bond between them. So for example, we have MgCO3, CaCO3, SrCO3, BrCO3. As you go down the group, since they become more thermally stable, so we need more energy to break the bond. As a result, it becomes more endothermic. So that is statement number one. Okay, the H decomposition becomes more positive down the group. All right. Next, the size or ionic radii of the oxide ion is smaller than the carbonate ion. That I've already mentioned beforehand clearly, because oxide is just one atom while carbonate on the other hand is much bigger. Okay, so that's another thing which we need to consider. Now finally, what is our last one? If you wrote these 2 points, that would be more than enough because it's just worth 2 marks since it's the first time that it came. Now the lattice enthalpy of oxides becomes less exothermic faster, or less negative faster comparatively. Okay, it changes more. So what does this exactly mean? What significance does this have? Check this. Let me draw some this is basically the enthalpy change for decomposition, the cycle that we're going to use. So let me just write this down. Suppose we have magnesium oxide, then we have calcium oxide, strontium oxide, barium oxide. Fine. On the other hand, maybe we have magnesium carbonate, then calcium carbonate, then we have strontium carbonate and barium carbonate. Now think about it, I'm not talking about the decomposition. The del H decomposition becomes more endothermic down the group because the bond strength increases, right? it becomes harder to break, so we need more energy. Now I'm just talking about the enthalpy change, the lattice enthalpy, the energy released when 1 mole of a compound is formed from its constituent gaseous ions. Now, the stronger the bond, okay, the stronger the bond, the higher the lattice enthalpy. So clearly, over here, the stronger the attraction between cation and anion. Since this is the smallest, all of these have a charge of +2. And since magnesium is the smallest, it will attract O the most. The bond formation that will occur when this happens, Mg2 plus O2 minus, the energy that is released, del H, is negative, okay? So I think it's best if I just show you the actual values. Let me just bring them out. Lattice enthalpies of group 2 oxides. I'll show you the exact values, then you will get a better idea. 3890, it is minus 3890, then it is minus 3460. All of these will in fact be negative. Minus 3217, and BRO, sorry, BAO, minus 3054. Fine, that's good. Now let's talk about the one for carbonates, okay? So firstly we have MgCO3, it's minus 3425.2. And calcium is minus 3163.5. So yeah, I can't really find the ones for strontium carbonate and barium carbonate. I'll still try, but it would be better if we had numerical values. But you guys get the trend that it becomes more endothermic down the group. It's just that, look at this. Look at the trend for oxides. 3460 minus 3890. How much is the gap? It's 430. But for carbonates, it's 3425.2 minus 3163.5. How much is that? 261. Both of them are becoming more endothermic down the group. Both of them are becoming more endothermic down the group. It's just that oxide is increasing at a faster rate. Okay, the reason being the ionic radii, or the size of the oxide ion, is smaller than the carbonate ion. So it actually attracts the, you know, cation more strongly. So if the cation becomes bigger, the impact is greater, essentially, okay? So that's the concept that you need to know of over here, that due to the difference in size between carbonate and oxide, since oxide is smaller, the impact on the change is much greater for the lattice enthalpies as you go down the group. So think about it, if I did the first one, okay, if I did the first enthalpy of decomposition for the del H decomposition for MgCO3, for example, what would we be getting? Check this. I'll show the math. So it would basically be minus 3890 minus plus 3425.2 plus this del H constant, minus 3890 plus 3425. So that is basically minus 465 plus del H. What is this del H actually that I wrote beforehand? It's basically the conversion of the carbonate ion to one oxide ion and one molecule of carbon dioxide. Essentially what happened over here. See, group 2 carbons decompose when heated to form the metal oxide and carbon dioxide. Suggest a mechanism for the decomposition of the carbonate ion by adding two core layers. This is the equation essentially that I wrote over here. As you can see, the carbonate ion, the cation remains the same. It's just that the carbonate ion decomposes to form carbon dioxide and oxide. Okay, so this is essentially the one that we are looking at. Simply put, this is the equation that's occurring over here as well. Do you guys understand? So I'm just thinking that could we draw a better His cycle, because the one up there is also decomposition. But yeah, this thing over here should be a constant. The change for the carbonate ion essentially. While enthalpy of decomposition, it is a different thing. It will change depending on the cation that it is attached to, right? That also plays a role over here. So the question is, why do they change by different amounts? Essentially, if we analyze the question, they wanted a few things. Firstly, suggest how the standard enthalpy change of decomposition for group 2 carbonates increases or changes down the group. I just told you that as you go down the group, the bonds of attraction become stronger. As a result, it takes more energy to break, so it becomes more endothermic or more positive. So that is how we get 1 mark. Then they've asked us to explain your reasonings in terms of the relative sizes of the anions. Okay, so yeah, to answer that, I just told you guys that the size of the oxide ion is smaller than the carbonate ion. So that checks box number 1. And then they want an answer in terms of the relative changes in lattice enthalpy. So we can say that the lattice enthalpy of oxides has a greater impact. It changes more, or it becomes uh, more positive or less negative faster comparatively. And why does this matter? Check this out. If I perform the calculation for oxides, it is this value over here. Now, if you perform the same calculation for, maybe calcium carbonate, what would it be? Essentially, it's lattice enthalpy of the oxide, which is minus 3460 plus 3163.5 plus del H. So let's do the math. Minus 3460 plus 3163.5, that is minus 296.5 plus this constant value of H, which is also going to be positive since we are breaking something down. But yeah, this is the logic behind it. And as you can see, as you keep on going further down, look at this value over here. This is a positive value, and the negative value is becoming more positive faster. Why? It's because the lattice enthalpy of the oxide is changing at a faster rate compared to the lattice enthalpy of the carbonate. Both of them are becoming positive. That's what you need to get. Okay, kind of like lattice enthalpy and hydration enthalpy. You already know the drill for hydroxides and carbonates. Both of them, both lattice and hydration actually become more endothermic or less exothermic down the group. Okay, but it's just that one changes more than the other, right? It's kind of like that. So essentially here we have the same concept. But I'm just thinking that whether we could draw another His cycle. Let me try. So for example, we have calcium carbonate. It's gonna break down to form calcium oxide plus CO2. This is del H decomposition. The problem is in the enthalpy of solution cycle, we could connect hydration and lattice. But here both of them are lattice enthalpies. That's the hard part. So we can't really connect them. Do you understand the issue? Because we need different cations and anions. We have calcium on both sides, but on the left side we need carbonate and on the right side we need oxide. So that's the issue. That's why we need this extra part that's connecting them, like a bridge. Okay, converting the carbonate to oxide and carbon dioxide. That's the issue. But anyway, I hope you get the gist, the reasoning behind the answer. We know why it becomes more positive, And why do they change by different amounts? Because one anion is smaller than the other one, and due to that the lattice enthalpy of oxides actually changes faster. Okay, that's the logic. So we spend a lot of time there. Let's move on to part C. Potassium sulfite K2SO3 is used as a food additive. The concentration of sulfate ions SO3 2- can be determined by titration using aqueous acidified manganese ions MnO4-. 250 cm cube solution contains 3.40 grams of impure K2SO3. 25 cm cube of this solution requires 22.4 cm cube of 0.0250 mol per dm cube acidified MnO4 to reach the endpoint. All the SO3 2- sulfite has been oxidized. None of these species is in the impure K2 theory are oxidized. Okay, potassium sulfite. Two half equations are given. To balance it out, we know that we need to multiply this by 5 and this by 2. We essentially need to balance the number of electrons. So let's do that. So on the left hand side we have 2 MnO4 minus plus 16H plus, can get rid of the electrons, plus 5H2O plus 5SO3 2 minus. That's on the left, and on the right we have 5SO4 2 minus as well as 10H plus plus 2 Mn2 plus plus 8H2O. Okay, so now we can just do some editing, because we know that there's 16H plus on the left and 10H plus on the right. So we can actually reduce this, get rid of it. 16 minus 10 is 6. So we end up with 6H plus. Similarly, we have 8H2 on the right and 5H2 here. So 8 minus 5 is essentially 3. So that's 3H2O. So this should be our equation after a lot of simplification. Let's check with the mark scheme. 2 MnO4 minus plus 6H plus. Oh, that was the plus sign for H, my bad. Plus 5SO3 2 minus is equal to 5 sulfate plus 3 water molecules plus 2 Mn2 plus. Alright. Calculate the percentage purity of the sample of potassium sulfite. Okay. So 25 cm cube of that solution out of the 250 required this much amount of permanganate. So it's been diluted. Let's do the math. So according to the molar ratio, what's the moles of MnO4 minus? That is 22.40 by 1000 times 0.0250. So 22.4 by 1000 times 0.025 is equal to 5.6 into 10 to the power minus 4. That's good. Now, what about the moles of sulfite SO3 2 minus? According to the molar ratio, it's going to be 5.6 into 10 to the power minus 4 divided by 2 times 5 by 2 times 5, which is 1.4 into 10 to the power minus 3. Fine. Now we are going to find out the moles in the initial 250 cm cube. Now we're going to find out the moles in the initial 250 cm cube solution. That is going to be 1.4 into 10 power minus 3 times 250 by 25, which is 10 times. That is 0.014 moles. Fine. Now what do we need? We want to find out the percentage purity of the sample. Fine. So we need to find out the mass. So for that we need the MR, and which is why I'm gonna manage the periodic table for you guys. Wait, where is it? Here you go. Okay, so it's K2SO3. So potassium is 39.1. So the mass of K2SO3 39.1 into 2 plus sulfur is 32 or 32.1? It's 32.1. 32.1 plus 48, that is the MR, times 0.014. So 39.1 into 2 plus 32.1 plus 48 is 158.3. 158.3 times 0.014, that is 2.2162. Now let's find out the percentage purity. How much is it? 2.2162 divided by the original mass of 3.4 grams, right? 3.40 grams into 100, that is 65.2%. Okay, according to my answer, it is 65.2%. So see if you guys got it. If you have any queries, please do comment below. Potassium disulfide is another food additive. The disulfide ion has the displayed formula shown in figure 1.2. Deduce the geometry around the sulfur, alpha sulfur atom in S2O5. Okay, so let's do the hybridization. It has 1, 2, 3, 4 bond pairs. Essentially, we do not consider pi bonds, and sulfur is in group 6, so 1, 2, 3, 4, 5, 6, all 6 electrons are used. So if you have 4 bond pair and no lone pairs, how much is that? The hybridization number is 4, and since it's 4bp 0lp, it's just like methane, so it's going to be, the geometry is tetrahedral, and the bond angle is 90°. It's just like methane because it has 4 bond pairs only, and we do not consider pi bonds, we only consider sigma bonds, right? Question 2, state 2 chemical properties of a transition element. So we know that they have multiple oxidation states, so they have variable or multiple oxidation states. Then we know that they can act as catalyst, they behave as catalysts. Then others include they form complex ions or complexes, and the last one is they form colored compounds. They form colored compounds or ions. So any two from these four. So define a complex ion. This is the most important definition that you'll find multiple times. What is it? A complex ion is a molecule. A complex ion is a molecule or ion formed by a central metal atom or ion, right, bonded to or surrounded by one or more ligands. Bonded to or surrounded by one or more ligands. Okay, where a ligand is a species which contains a lone pair and can form a dative covalent bond with the central metal atom. Now we have cobalt in our syllabus, and the colors are required. Okay, the colors for cobalt are required. It's really important. So cobalt, what is the color of cobalt? So you know that copper is blue in color, we all know that, and cobalt is pink in color. Okay, cobalt solution, aqueous solution of cobalt, is actually pink in color. So when you give aqueous ammonia, cobalt is actually soluble in excess ammonia, and it is going to form CO NH36, just like this. And if you give excess NaOH, it is actually not soluble, so it's going to form precipitate. Either you can go for COH2, cobalt hydroxide, or you could go for this complex COOH2 H2O4. I personally prefer the first one because it's easy. This is a blue PPT, this is a pink solution, and cobalt with excess NH3. It is like a, it's like a brown or yellow, solution. Okay, and what about excess HCl? So when you do this, you get a blue solution, and it's going to be COCl4, and it is going to have a charge of 2 minus in total, right? 2 minus, because each chloride is -1. So you need to compare and contrast this with copper, because the copper solution itself is blue. When you add excess chloride, it turns into a yellow solution. When you give excess NaOH, it turns into a pale blue PPT. When you give excess NH3, it turns into a dark blue or violet purple solution, right? Okay, so let's just write this down now. You know the answers. It is CONH3 6, still 2 plus. This was CO. Oh, you don't need to give a bracket here, my bad. Cl4 2 minus, and finally C is either COOH2 or COOH2 H2O4. Okay, so that is fine. Now, what is the color and state? I just told you that this is in fact a brown solution. Oh, they've allowed yellow brown. Okay, but just go for brown. Okay, brown is better. This is a blue solution, as I've told you, and excess of NaH gives you a blue precipitate. They've also allowed pink PPT, but go for blue PPT, that's better. Okay, now what are the types of reactions, right? So firstly, this is simply a ligand exchange, because one ligand took the position of the other. Similarly here, this is also ligand exchange. Chloride took the position of H2O, but on the other hand, excess of NaOH, this is a precipitation reaction. The ligand no longer exists, and we have a solid precipitate now. Okay, moving on to the next one. Ethane diet can act as a bidentate ligand. What is a bidentate ligand? You already know it. It is a species that donates or uses two lone pairs. Okay, why? To form two dative covalent bonds, or two coordinate bonds to a metal atom or ion. Fine, you need to memorize this definition. Now the complex COH2O to C2O4 BrCl minus exists as stereoisomers. So we have two water, uh, one ethane diet, one bromide, and one chloride. So we have one bidentate ligand. Okay, we have one bidentate ligand over here, and four other monodentate ligands. Now complete the three-dimensional diagrams in figure 2.2 to show four stereoisomers of this. The bidentate ligand is already shown. Okay, so that helps us a lot. So we are going to consider it from this aspect. So one of them being, what if we put the water molecules along a same line like this? Fine, this is one isomer. Clearly this is one unique isomer. Okay, now what about another one where we don't put them along the same line? So we have multiple options for that. For example, if I put the water molecule over here, and I can just exclude this position, right? I can just exclude this position and put it elsewhere. I can exclude this position and put it elsewhere. So what does that mean? Maybe I could put it over here like H2O, like this. And then one isomer where I have bromine here and bromide and chloride here. And there could be another isomer where I keep the waters in the same positions. However, I just exchange the position of chloride and bromide. That would also be a different isomer. See if you guys get this. These are two unique isomers. Okay. Now, what about this? The one where I kept the water close to each other in one line. Sorry, not close to each other, but rather than that, in one line. I could put chloride over here and Br over here. But you guys need to understand something. If you exchange their positions, like if you put Br over here and chloride over here, then it would still be the same isomer. Okay, this is not unique, but rather this one is unique. Okay, you guys need to get this, that this is in fact a unique isomer. Now there are honestly more. Let me just show you all the other ones. I need to copy this one. Wait, in total there are 6, I think. So what about the other ones? What if we put the H2Os in close proximity like this? And we could put bromine and chlorine in one line. Okay, like in the mark scheme there are chlorine and bromine like this, but remember that it would not be different if you put bromine and chlorine here. It would be the same isomer. Okay, you guys need to understand that. Okay, similarly, how you know if you exchange the positions of bromine and chlorine here, it won't really make a difference. It's the same isomer. But in this case, why does it make a difference? Because the dipoles will be different. Check this. Here there will be one kind of dipole, but here there will be another kind of dipole. That's why these are actually unique. But on the other hand, here the dipole is fixed. Okay, so being here or here doesn't really matter. It still produces the same compound. Similarly here, the dipoles are fixed. So if you change their vertical positions, it won't really matter. It's the same isomer. Okay, it's a bit hard to explain, but you guys need to appreciate that even if you change the positions of chlorine and bromine in these ones, it wouldn't really make another isomer, right? That's what you guys need to know, because the water molecules are already in one line. Okay, so it won't really make a difference. Now let's move on to the next one. What other variations do we have? I put them in one line. I put them side by side. There is one other combination that's lacking for the water molecules. Where can I put them? So these were the two possibilities. Either according to the mark scheme, this is what they've wrote. They gave this H2 1 H2 over here, 1 H2 over here. Okay, but you guys need to appreciate that the same thing could be possible for 1 H2 over here and 1 H2 over here. There basically needs to be a gap of one atom between them. Then it will lead to a unique isomer. So let's just go with the one in the mark scheme. This one gap. Fine. Now let's draw the isomers. So yeah, we could just change the positions of chlorine and bromine. Suppose I could put chlorine here and bromine here, then bromine here and chlorine here. As you can see, these are separate isomers. But you guys need to appreciate that I just showed you. Like if I kept one water molecule here and another water molecule here, and then I change the position of bromine and chlorine on these ones, it would still lead to the same isomers as these two that I've drawn here. So this is also a unique combination. You need to appreciate the differences that I'm going to repeat again. In one of them, we put the waters in one straight line. In the other, we kept a gap of one atom. And in the last one, we actually kept them side by side like this. Okay, these are the three variations. Now for the one where water is in a straight line, okay, so in totals actually there are more. Water in a straight line basically, and water in close proximity in the central one that is opposite to the bidentate ligand. Okay, for these ones there are no variations. Even if you change the positions of chlorine and bromine, you would end up with the same isomer, because no other, it won't produce a variation in the dipole moment. However, for the one where we keep water in close proximity, the other variation, here we keep them in close proximity opposite to the bidentate ligand. Here we keep them in close proximity, like you could keep them here or you could keep them here and then just change the positions of bromine and chlorine there. You end up with a unique isomer. Like if you keep it like this and then change the positions of bromine and chlorine, you get two isomers. Similarly, if you put a gap of one atom, you could put them here, or you could put the water molecules in these two and then change the positions of bromine and chlorine, you would end up with different isomers like that. Okay, but they would be the same compound. Like if I drew it this way instead, what if I drew this? Suppose H2O. H2O, they did not include this in the mark scheme, but it is also valid. H2O, then chlorine, bromine, then you could just change the positions, bromine, chlorine, like this. That would still result in a correct answer. Okay, so I'm coming back to the correct one. Chlorine and bromine here. H2O, H2O, fine, that is it. So hopefully you guys get it. Now state the oxidation state of cobalt in this complex. Okay, so bromide is -1, chloride is also -1, water has no charge, and what about ethane diode? It's -2. So in total that's -2, -2, and plus x is equal to -1. So plus x minus 4 equals to -1, so x is equal to +3. So the oxidation number of cobalt is +3 actually. And what is the type of stereoisomerism that we are seeing here? Clearly, like, there are a lot of variations. Okay, for example, this one over here, where the water molecules are in a straight line, and the ones where they aren't, that is an example of geometrical, or essentially cis trans isomers. But the other ones, they are examples of optical isomers, because here you are seeing a few which are actually mirror images of each other. Okay, for example, this is the trans isomer clearly, and the other ones are the cis isomers, the ones where water isn't in a straight line. All of them are the cis isomers. But we are also seeing optical isomers because we are getting mirror images of a few ones. For example, if I compared them, like maybe this one, right? This one over here is actually an optical isomer of this one. It's like a mirror image. Similarly, these two are optical isomers of each other, and these two are optical isomers of each other. And clearly this one is the trans isomer and this one is the cis isomer. You could also consider the other ones to be cis, but the trans one is fixed. Okay, so it also has optical, so you could opt for any one since it's such a unique compound. This is the first time I've seen this. I haven't seen this before. Good variation. Moving on to question number 3. So how many questions are there in total? I haven't checked the paper yet, so let's check it out. In total there are 9. Okay, so we are gonna be done hopefully within 2 hours or 1 hour 30 minutes. Complete table 3.1 by placing one tick to indicate the sign. Bond energy. Okay, by definition bond energy is, by convention, it's defined as positive. Enthalpy of atomization is always bond breaking positive. Enthalpy of formation can actually be both. Define standard enthalpy of atomization. Okay, we know it. It is the enthalpy change when 1 mole of gaseous atoms is produced, okay, from its elements in its standard state, in its standard state. From its element, we could go for element in standard state, or from its elements in their standard states, right? Or you could say under standard conditions, same thing. Or at 298 Kelvin and 1 atm, same. Okay, it's up to you guys. Next, what do we have? I think we have a Born-Haber cycle. Calculate the lattice enthalpy of Ag2O using relevant data from the table. Fine. So let's draw the basic cycle first. So we know that we are going to start with silver solid, two of them at that, and one oxygen atom. So that's half O2 gas. So the arrow downwards is going to be Ag2O solid, and the arrow upwards is going to be, firstly, we are going to atomize silver. Then we are going to ionize it, 2Ag plus gas. Then we are going to atomize the oxygen atom. I need more space. What next? Next, I'm going to perform the electron affinity. So as you guys know that the first electron affinity of oxygen is negative, always. The first electron affinity is going to be negative, O minus gas, but the second one is going to be positive again. And finally, we are gonna go to the lattice enthalpy. So this is del H lat over here. This is the first electron affinity of oxygen. This is the second electron affinity of oxygen. And yeah, this is the del H atomization into 2 of silver basically. This is del H IE first of silver into 2, and this is del H atomization of oxygen, which is half the bond energy, right? Because we're getting one oxygen. Fine. So let's just input the details now, then it should be fine using relevant data. So what is the ones I'm going to use? First, ionization energy of silver, then bond energy of this, first electron affinity of oxygen, second one, I don't need this one, and formation of silver oxide and atomization of silver. These are what we need. Okay, fine. So let's do it. So firstly, I need atomization of silver, 285 followed by 731. So that is 285 into 2, then 731 into 2. Then what is atomization of oxygen? It's going to be half the bond energy, because I need one oxygen atom, which is 496 by 2. How much is that? 496 by 2. 248. 496 by 2, which is 248. Then finally EA, minus 141 plus 798. Minus 141 plus 798. No multiplication here since one oxygen atom. And then finally minus 31. That is the it is the lattice enthalpy. No, it's formation, my bad. It's the del H formation of silver oxide, so that is minus 31. So let's do it now. So let's do the math. So according to the Hess cycle, we know that this is equal to the rest of them, right? So we can write that minus 31 is equal to 285 into 2 plus 731 into 2 plus 496 by 2 minus 141 plus 798 plus del H lat. Okay, fine. Therefore, del H lat is equal to minus 31 minus 285 into 2, minus 731 into 2, minus 496 by 2, plus 141, minus 798. That gives me an answer of minus 2968. Minus 2968 looks perfect. Minus 2968. Awesome. So this is the trend in the magnitude of lattice energies of the silver compounds Ag2S, Ag2O, and Ag2Se. So we have the same cation, but Ag2S, Ag2O, and Ag2Se. So basically we are going down the group. They've just confused us. Look at this. So we have oxygen first, followed by sulfur, then selenium. As you go down the group, the lattice enthalpy actually becomes more endothermic. So which is the highest magnitude? The most exothermic is clearly the one at the top because it has the smallest size. It should be Ag2O over here, followed by Ag2S, and then Ag2Se. The logic being the size of the anion increases down the group. The radius or size of the anion increases down the group. Or you could, there were alternate answers, charge density of anion decreases down the group. Or you could say that O2 has the smallest radius. So what is the second point that we need to write? That there is less attraction. Less attraction between the ions, or you could say that the ionic bond gets weaker. The ionic bond gets weaker with Ag2Se. Fine. Now we have silver sulfite Ag2SO3 soluble, which is sparingly soluble in water. Given expression for the solubility product of Ag2SO3. So it's pretty straightforward. We know that Ag2SO3 is sparingly soluble, so it forms 2Ag plus aqueous plus SO3 2 minus. So it is essentially Ag plus whole square times SO3 2 minus, like this. Calculate the equilibrium concentration of Ag plus in a saturated solution at 298 Kelvin, where the Ksp is this. So we know that Ksp is equal to 1.50 into 10 to the power minus 14. So for the Ksp, we can actually consider this to be x, this is also x, and this is twice x. So what is it exactly? Twice x whole square times x, right? Twice x whole square times x is equal to 1.50 into 10 power minus 14. Or it is basically 4x cube is equal to 1.50 into 10 power minus 14. Or followed by x is equal to 1.50 into 10 power minus 14 divided by 4 cubic root. So how much is the answer? 1.5 into 10 power minus 14 divided by 4 cubic root of answer. That gives you a value of 1.55 into 10 to the power minus 5 mole per dm cube. That is the concentration of sulfite as well as Ag2SO3. That's the solubility basically. Now for Ag, we know that Ag is twice of this. So the concentration of Ag plus is 2x, which is 2 into 1.55 into 10 power minus 5, which gives you a value of 3.11. 3.11 into 10 power minus 5. Okay, mole per dm cube. Hopefully that's fine with you guys. Next, the standard enthalpy change of solution of AgNO3 in water is 22.6 kilojoule per mole. Suggest how the feasibility of dissolving AgNO3 in water changes with temperature. So it's this one is soluble in water. Now it's an endothermic reaction. So if we increase temperature, we know that the equilibrium will actually shift to the right, and the feasibility will increase because the chance of forming aqueous ions actually increases. So we have to say that feasibility increases as temperature increases. Feasibility increases as temperature increases. That's point number one. So here you need to actually talk about entropy or else you won't get marks. So we know that when does a reaction become more feasible? When del S is more positive and del G is more negative, right? So here we can say that del S is positive, right? Or the entropy change or del S is positive now. Or you could say that minus T del S becomes more negative. Or you could say that plus T del S becomes more positive. Same thing. Because this dissolving in water, the entropy change is already positive. And we know that del G is equal to del H minus T del S. So think about it. Del H is already positive. Sorry, T del S. And del S is also positive. So as you increase temp, what happens? The value of T del S will increase in magnitude, and minus T, since del S is positive, as you increase temperature, the value of minus T del S becomes more negative. So when this section will overtake this one on the left hand side, del G becomes more negative, right? So that is exactly what we need to say. Therefore, why? As del G becomes negative or less than 0. Okay. So feasibility increases as temp increases because as temp increases, either T del S becomes more positive or minus T del S becomes more negative. And del S is positive from the beginning. And overall, the ultimate result is del G becomes more negative. Fine. Question number 4. I actually had a part of it done. But let's start from the top again. What is meant by the overall order of reaction? So it is actually the power, right, to which the concentration of a reactant is raised. It is the sum or total of the power or you could say that it is the exponent to which a concentration of a reactant concentration of a reactant is raised in the rate equation. Or law. Fine. In the rate equation or law. Now use the data in the table to deduce the order of reaction with Fe3 plus and with I minus. Okay, so if we use experiments 1 and 2, see, as you've increased the concentration of Fe3 plus by 3 times, the rate also increases by 3 times. So it is first order with respect to iron. Okay, so we're going to mention that using experiment 1 and 2, when the concentration of Fe3 plus increases by 3, rate also increases by 3. So first order with respect to, you need to give the dots Fe3 plus. That's good. What about the next one? Now for iodide, we actually have multiple options. We can go for 1 and 3 or 2 and 3. It's up to you guys. So let's go for 2 and 3 honestly. Or we could go for 1 and 3 as well. Check this out. So from 1 to 3, what happened? The concentration of Fe3 plus doubled, and the concentration of iodide also doubled. So due to this double, we know that it will turn to 2.622, which is 5.28. It turns into 5.28 into 10 to the power minus 4 already. So we need to compare this and this. So iodide doubles. So what will this be? 2.11 into 10 power minus 3 divided by 5.28 into 10 to the power minus 4. So 2.11 into 10 to the power minus 3 divided by 5.28 into 10 to the power minus 4, which is 3.996, or basically 4 times. So what happened to rate? Due to the doubling of Fe3 plus, is doubled, and now due to the doubling of iodide, it became 4 times. So when iodide was doubled, it became 4 times. So it is second order with respect to iodide. Okay, so that's the important part. So next one, using experiment 1 and 3, right? I used 1 and 3. When concentration of Fe3 plus, you have to find out the order of Fe3 plus first, or else this won't work. When it became doubled and iodide also became double, rate turned into 2 times 4, which is 8 times. So it is second order with respect to iodide. Fine. Use your answer to construct the rate equations. So rate is equal to, you know the drill, K times concentration of Fe3 plus first order times concentration of iodide whole square. Yeah. So what is the overall order? It is 3. 2 plus 1, 3. Now deduce the value of K from experiment 1 along with the rate constant. So the initial rate is 2.64 into 10 power minus 4. 2.64 into 10 to the power minus 4 is equal to K times, what's the concentration of Fe3? 0.04. 0.04 times 0.02 whole square. Okay, so if we do find that out, what do we get? K is equal to, after you divide it, 2.64 into 10 to the power minus 4 divided by 0.04 divided by 0.02 whole square, 16.5 actually. And what is the unit? We know that rate has a unit of mole per dm cube, and below it's actually mole per second rate, and for that it's mole per dm cube times mole square dm minus 6, which is mole cube dm minus 9. So after simplification, it turns into mole minus 2 dm plus 6 and second minus 1. So mole minus 2 dm6 second minus 1. Perfect. Describe qualitatively the effect of an increase in temperature on the rate constant. So you know that temperature actually increases the value of K. So K and rate of reaction both increase. Okay, it is always remember that it is directly proportional. So both K and the rate of reaction will increase. In aqueous solution, iodide ions react with acidified hydrogen peroxide as shown. The initial rate of reaction is found to be first order with respect to iodide, first order with respect to hydrogen peroxide, and zero order with respect to H. Okay. So it is first order with respect to iodide and first order with respect to H2O2. So it is essentially rate is equal to K, 1 iodide and 1 H2O2. So our slowest step should include 1 iodide and 1 H2O2. So clearly our slowest step is step 1, since look at it, it contains 1 iodide and 1 H2O2. You know that if you have multi steps, the slowest step is the one which determines the rate, and it will be consistent with your rate equation. Okay, like if the order was 2 for iodide, we would have 2 iodide ions instead. So what is our answer? It is going to be step 1. And what is our reasoning? As this has 1 mole of H2O2 and 1 mole of iodide. Is that fine? Or you could just say that it has correct stoichiometry, or the number of moles of each reactant are consistent with the rate equation. Okay. Step 1, as it has correct stoichiometry or coefficients of 1 H2O2 and 1 I minus. Yeah, identify a step that involves a redox reaction. Okay, interesting. So here, look at step 1. You know that in hydrogen peroxide oxygen is -1 and in water oxygen is -2. So I think we have our answer. It's step 1. Step 1. Why? Firstly, because oxidation number of oxygen changed from -1 to -2. And also look at the oxidation number of iodide. It changed from -1. And look at iodide over here. It is -2 over here, oxygen. But iodide has an oxidation number of +1. So iodide was oxidized actually. So step 1, because iodide for iodine, the oxidation number changed from -1 to +1. And oxygen, oxidation number changed from -1 to -2. Apparently there's another one. Check out step 3. Iodide changed from -1 to 0, and oxygen changed from, oh no, it's a disproportionation reaction. And here hydrogen is +1, oxygen is -2. Iodide changed from +1 to 0. Okay, so for its the change is for iodide here. For iodine, it changed from -1 to 0 as well as from +1 to 0. Okay, so for step 3, this is an alternate answer. You just need to write 1. Iodide oxidation number changed from -1 to 0, and also iodide oxidation number, iodine actually changed from um, +1 to 0. Hopefully I could clarify. So just the role of HIO in this mechanism. What is HIO acting as? Basically HIO was formed and then formed in step 2 and then used up in step 3. So what is it acting as? Basically an intermediate. So in a multi-step reaction, these are called elementary reactions. Anything that you find in between and that is used up again later, that thing is called an intermediate. Or you could also consider it to be, look at this, what is the role of HIO here? HIO is actually converting, right, iodide to iodine. It is oxidizing iodide to iodine. Okay, so that is very important. So any role works. The first one being, it is acting as an intermediate. Why? Because it is formed in step 2 and used up in step 3. Fine. Also, what is an alternate answer? It is acting as an oxidizing agent in step 3. Oxidizing agent in step 3, as it oxidizes iodide to iodine. Fine. Okay. Moving on to question number 5. We have 5, 6, 7, 8, 9 left now. 5 questions. Hopefully it'll be done soon. So it's going to be reduced. There you go. So we just lose the benzene ring, and when you add bromine with UV light, it is actually going to be a free radical substitution reaction. The ring won't take part in the reaction. Okay, the ring will not take part in the reaction, but rather the CH3 that you have here, it will turn into CH2Br. One of the hydrogens will be replaced by bromine, free radical substitution. And when you add bromine to the equation, you know that alkyl groups are orthopara reacting groups. So positions 2, 4, 6. So what will happen? We already have this over here. So it can either be added to group 2 or group 4, because honestly in disubstituted rings, right, position 6 doesn't matter. I'll tell you what I mean by that. Because if you draw the bromine over here, it would still be 2-bromotoluene, right? So what is a unique isomer if you put it in position 4 like this? So this is 4-bromotoluene and this is 2-bromotoluene. Good. Complete table 5.1. What is the type of reaction for step 1? I just told you that hydrogen is a reducing agent, so it's a reduction. They also accepted hydrogenation, it seems. Hydrogenation. And for reaction 2, what is the type they've asked? Type. It's basically no, what's the mechanism? The type is substitution, but the mechanism is free radical substitution, right? So free radical substitution. Fine, awesome. And what about reaction 3? The mechanism is Friedel-Crafts. Sorry, the mechanism is electrophilic substitution, okay? And this is just the type is halogenation. When methylbenzene reacts with an electrophile, a substitution reaction occurs. No addition takes place under these conditions, unlike typical alkenes. Why is that? Because basically, if this is more stable, the benzene ring is more stable than the product of addition. That's the main answer. The benzene is actually stabilized by this delocalized system of pi electrons. So what can we write over here actually? Let's do it. This is what the Mark scheme wrote. The substitution product is stabilized by delocalization of pi electrons, or you could just say by pi electrons in the ring. Fine. Or you could talk about the negative point, that the addition product, the one I was telling you guys, the addition product is not stabilized. The addition product is not stabilized by delocalization of pi electrons. They've also allowed another point. They wrote addition product will remove pi electron delocalized system, which kind of makes sense. Yeah, just true in another way. The reaction of methyl benzene with thionyl bromide SOBr2 in the presence of an iron 3 bromide catalyst is shown. The mechanism of this reaction is similar to that of the bromination of benzene. Fine. The first step of the mechanism is shown, formation of the electrophile using FeBr3 catalyst. The reaction of methyl benzene with SOBr3 ions is shown. Complete the mechanism. Okay, let's do it. So you know that the electrophile attacks the nucleophile since it's electrophilic substitution. However, arrows will always be drawn from the nucleophile to electrophile, and it has to be a curly arrow. So that's how you get your first mark. And then to get the second mark, we need to draw the intermediate, yeah? How is it drawn? I taught you in my previous videos. So it's gonna attack this particular carbon over here. This carbon over here, right? So we have to draw the ring of delocalized electrons. It won't cover all carbons now. It will cover 5 carbons. All of them except this one over here. And we know that this carbon has a hydrogen attached, as well as this new bond that it just formed, like this. And this one is positive inside because 1 electron from the ring was donated to SOBr3. But now the final step is heterolytic fission of this bond to replace the electron that has been lost, and at the end we just release an H plus. That is the most important part. Okay, so see if you get this diagram. This is really important. An electrophilic substitution mechanism will be there in your exam. You need to master it. Okay, you can check out my A-level organic chemistry part 2 video up top. I'm gonna link it over here. All the mechanisms are discussed at the end. Anyway, moving on to part 3. The reaction shown in figure 5.2 produces a small amount of a byproduct P with the molecular formula C14H14OS. C14H14OS. So clearly C14H14, it clearly has a 2 ring two ring structure. Okay, so we need two rings. So interesting. How can you get two rings? So clearly SOBr2. What is SOBr2? SOBr. So in this reaction, what happened? The benzene ring took the position of this. So isn't it possible to undergo another substitution? Maybe the benzene ring can take this position, right? Both of them might be substituted, like this compound. Here we can take the position of this bromine with another benzene ring. So let's try doing that. We can draw sulfur here, and we already had benzene over here like this. Okay, we already had this. Now we're gonna have another benzene ring like this. Here you go. Okay, so this is the product. Or there was another possibility, the reaction in 5.2, this one produces another byproduct. There could be a possibility that, maybe it wouldn't join in position number 2 of the benzene ring. Maybe it would join in position number 4. So they've allowed another byproduct, which is basically this, the same thing, but just a bit different, like this, SO. And then if you draw the benzene ring, it went to position 4 like this. This is also fine. Position 1, 2, 3, 4. That's also okay. But I honestly go with this. Easier to draw, right? Okay. Acyl bromides, RCOBr, can be synthesized by the reaction of a carboxylic acid and SOBr2. This is a similar reaction to the synthesis of acyl chlorides using thionyl chloride. Given equation for the reaction between ethanoic acid CH3COOH plus SOBr2. So we are going to end up with it's a thionyl bromide basically, SOBr2. We're going to end up with the acyl bromide CH3COOBr plus, what do we get? In thionyl chloride, we get HCl and SO2. So instead here we are going to get HBr instead of HCl, but still SO2. Now suggest the relative ease of hydrolysis of acyl bromides, acyl chlorides, and acyl alkyl chlorides. So clearly acyl chlorides and acyl bromides will be hydrolyzed more easily than the alkyl chlorides, clearly. But now let's take a look at the acyl bromide and acyl chloride. How do they differ? So first things first, basically, who is more electronegative? Clearly the chlorine atom. Chlorine is more electronegative than bromine. As a result, this is del minus, this is del minus, and this is del plus on um, you know the carbon atom over here. A similar instance occurs over here because the bromine is electronegative and this is del plus. On the other hand, for any acyl chloride, what is it like? What is it like? It is R is directly connected to chlorine. Okay. So how do we approach this? Here, basically, like, let me draw it in a better way. R CH2Cl. This is basically it. So the chlorine will be pulling it. So the carbon will also have a positive sign here, del plus. So it will be a target for nucleophiles, but not. It won't be as good of a target as these two over here. So which is the best target actually, comparatively? Honestly, the correct answer is, you might be thinking, okay, chlorine is more electronegative, so it might be the acyl chloride, but it's actually the acyl bromide. I'll tell you why. So acyl bromide is easiest, followed by the acyl chloride, and finally we have the alkyl chloride. So why so? Essentially, um, the CBr bond is the weakest here. Why? It's kind of like that question, the one we had in is HCl, HBr, HI. What happened to the bond energy, or CX bond, as we went down the group? Honestly, the bond length basically increased due to the larger size of the bromine atom, right? So the bond energy actually decreased down the group due to the increased length, due to the bigger size of the atoms themselves. So similarly, we have a similar answer in acyl bromides. CBr is much weaker. Why? Due to less orbital overlap, or due to Br having a larger atomic radii. Okay, so that is the point in favor of acyl bromide. Then for acyl chlorides, or in general, why are acyl halides easier than acyl chlorides? So the carbon in acyl halides, or you could talk about CCl or CBr or CX, much better, is more del positive, right? Is more del positive, or electron deficient, is more electron deficient. Or you could say that the CCl or CX or CBr bond is weaker than CCl in alkyl chlorides. But why is that? Why is that? We need to give an explanation, right? Nothing works without an explanation because it is attached to two electronegative atoms, right? I was telling you the oxygen as well as the halogen. Let me move this. Because it is attached to two electronegative atoms, or you could say due to electron withdrawing effect, due to electron withdrawing effect of the CO group. Fine. So that is that. And finally, why are acyl or alkyl chlorides the hardest to break? Mainly because the CCl bond is strengthened. In alkyl chlorides, the CCl bond, it is strengthened. Why? Because there is an alkyl group attached to the CH2, which actually makes this del plus less intense. The CCl bond is, rather than being weakened, it is strengthened. Okay, by what? By electron donating effect or positive inductive effect. By positive inductive effect or electron donating effect of the alkyl group. Okay, really important question. First time I've seen this. Usually we do get aryl chlorides, acyl chlorides, and alkyl chlorides. Aryl chlorides are unbreakable, they can't be hydrolyzed due to the delocalization of the lone pair in the benzene ring. But this is the first time that I saw an acyl bromide instead. Okay, so this point is new. This point over here is new. It is much weaker due to less orbital overlap of bromine due to its larger size. Next one, question number 6, 6, 7, 8, 9. We have 4 left. It never ends. That's why I hate solving chemistry before. It requires the most effort to solve. Although these questions look smaller compared to the other ones. Okay, so we are dealing with perindopril. It's a calcium channel blocker. I read this. I read this in pharmacology. It's a drug used to treat heart disease. State the number of chiral carbons present in one molecule of perindopril. Fine. So let's look for chiral carbons. Clearly, this is chiral. Then this one over here is chiral. This is chiral. Anything else we've missed? Now, this one over here is chiral. because it is attached to hydrogen over here, and up top it has nitrogen, below it does not. And this one is also chiral. It has hydrogen on one side, then below it's unique, above it's unique. Okay, so these are our five chiral carbons in total. So I'm gonna mark them again if you haven't figured it out already. 1, 2, 3, 4, 5. This is it. So 5. So there's one benefit and one disadvantage of producing drugs such as perindopril as a single pure optical isomer. Okay, so usually one of the optical isomers, one of the enantiomers, has higher biological activity, or according to the Mark scheme, higher biological efficiency. Or you could say, yeah, activity is also mentioned. Activity of the drug. Or you could say that it has less side effects. Or it may be more potent. Smaller dose required. Okay, smaller dose required as drug more potent. These are benefits. Now, what is the disadvantage though? Basically, you need to separate the two optical isomers using an optical catalyst, chiral catalyst, optical catalyst. Sorry, because usually when you try to make one of them, it's like you get two in one. You can't choose to make one unless you use a catalyst. Okay. So the disadvantage is that there is the need to separate racemic mixture, that is an equimolar solution which has equimolar concentration of each enantiomer, racemic mixture into a single enantiomer or stereoisomer, or basically there's lower yield of the biologically active stereoisomer molecule, or we need this is the better one, need a chiral catalyst or enzyme. This is what I was talking about, yeah, to separate them in the synthesis. So it's more expensive. So it is more expensive since we need one. Name all the functional groups present here. Okay, so clearly we have a carboxylic acid group over here. Then this COO is an ester. This NH is an amine, more particularly a secondary amine. And this is a CONH, which is an amide. So we have a carboxyl group. Then we have an ester. We have an amide. And more accurately, sorry, I wrote amine here by mistake. More accurately, we have a secondary amine, which they did not mention, but they should have. Okay, so COO ester, COOH carboxy acid, CONH amide, and just NH is amine. A sample of perindopril is hydrolyzed with hot aqueous acid. Draw the three organic products. Okay, no problem. Let's draw that then. Wait up. I need the eraser. There you go. I'm just gonna copy this for you guys. Let's go. So let's see where the hydrolysis occurs, and it is acidic hydrolysis, by the way. Okay, so it will be hydrolyzed over here, then it will also be hydrolyzed over here. Now, what are the products? On the left hand side, this is actually the alcohol end. So we are gonna get a small alcohol like this. Just copy paste alcohol. And then on this side, I'm just gonna copy it. I'm gonna get the carboxylic acid since this is the acid end. Then I'm gonna copy it. I end up with an N over here, and there is an H here. Okay, and following this, I just draw the part below. I just copied this part, and then I go to the right and down, and then right again, and I have another carboxylic acid end. This is the acid end of the amide. And then I draw the amide, I copy paste it. I draw N. Shit, I need more space. Okay. So this followed by, I drew this picture, and overall here I just need to add one H over here, right? Because this is the amine end of the amide, you just add an NH. So they just wrote it like this. Although this isn't the truth, because we know that in acidic hydrolysis, for complete acidic hydrolysis, what will happen to the NH? They are Bronsted bases, so they will be accepting another proton. So this should have actually been NH2 plus, and this should also be NH2 plus. Although in recent times I haven't seen them mention that. Okay. Next, 7, 8, 9, last three questions. Explain why phenol is brominated much more easily. It is brominated at room temperature to give us a white PPT. Why is that? Because in phenol, the lone pair of oxygen actually takes part in the delocalization of the benzene ring, and the benzene ring is activated at positions 2, 4, and 6. So let's write that the p orbital, or the lone pair from the oxygen atom, is delocalized into the ring, or overlaps with the ring. That is answer 1, step 1. Then there is greater electron density. There is greater pi electron density, specifically pi electron density around the ring. Or I prefer this one more. It makes the ring more electron rich, or positions, which the one I was saying 2, 4, 6, it makes it more electron rich. Fine. And finally, so it polarizes electrophiles more easily. Okay, or you could say that it is an easier target for electrophiles. Iodine monobromide IBr reacts with benzene in the presence of an AlBr3 catalyst. Predict whether the ionic product will be bromobenzene or iodobenzene. So suppose if we had this Br2 plus AlBr3, what happens? We get Br plus and AlBr4 minus. So essentially here both of them are bromine, both of them have the same electronegativity, so we know that it's gonna be the same product. But check this out, what if we have Bri? Now here's the thing, Br is more electronegative, so it will pull it more strongly. So after heterolytic fission, we are going to end up with Br minus and I plus, and this will be the electrophile that attacks the benzene ring. So we are actually going to end up with iodobenzene. This is so important, very unique question from CIE. Why? As Br is more electronegative. As Br is more electronegative than I. Okay, so the electrophile formed is I plus. Now 7.1 shows some reactions of phenol. Give an equation for the reaction of phenol with sodium. Pretty straightforward. What do we get? Essentially, it is C6H5OH plus sodium solid is equal to C6H5O minus Na plus, and we are gonna get hydrogen gas. Okay, effervescence of hydrogen gas, which pops the light at speed. Draw the structure of the ionic product R when phenol reacts with excess bromine. This one I told you about the white PPT. Yeah. So we have this is an equation that you all know of. It's the most common one. So this is the white PPT. Bromine will attach to the positions of 2, 4, and 6. State the reagents and conditions for reaction 1 and 2 respectively. So what is reaction 1? It is the formation of nitrophenol, 4-nitrophenol. So simply we know that phenol is activated, so we don't need concentrated HNO3 and concentrated H2SO4. It will simply react with dilute acid under room conditions, right? So we can just say aqueous or dilute HNO3, and you don't even need the acid catalyst H2SO4. Just dilute HNO3 is fine. And for reaction 2, this is actually an azodite. This is the azo group. So we've actually reacted, right? We've actually reacted this compound, this diazonium salt, N3 plus. We reacted this diazonium salt. You could draw the chloride along with, you actually added NaOH aqueous to activate the phenol, or else you need phenoxide first. Okay, so I added this diazonium salt and I activated the phenol with aqueous NaOH, and the two of those reacted to form an azo dye. So for reaction 2 we actually need alkaline conditions, so you need to mention alkaline conditions, or more specifically NaOH to activate the phenol, and we obviously need the diazonium salt, which is C6H, what is it? C6H5, yeah? C6H5 N2 plus Cl minus. You can drop the Cl minus, or you could just, draw it, or you could just draw this. That's fine. No one cares. This thing over here, and the plus is on here, right? That's fine, or you could just draw in 2 plus. This is the more accurate one, triple bond end with the plus on the left side, but they accepted other ones, but this is the correct one. Or you could just say alkaline NaOH and phenyl diazonium salt. Okay, phenyl diazonium ion or salt. Okay, anything works. This one is the best one. Moving on to the last two. They just wanted to include phenol in the question, as it seems. Okay, question number 8. We are almost there. Describe the difference in reactivity between chloroethane. Wait, how much marks does this have? 15 is pretty big. So describe the difference in reactivity between chloroethane and chlorobenzene with OH minus. So chloroethane, CH3, CH2Cl, and chlorobenzene. So clearly this aryl halide won't be hydrolyzed. No reaction. Okay, no reaction. So chlorobenzene is less reactive than chloroethane. Duh. Why? Because I was telling you guys that the p orbital, right? The lone pair on chlorine, the lone pair on chlorine will overlap or delocalize into the ring. Same answer. So it has a partial double bond character, right? So due to the partial double CCl bond, or you could say that the CCl bond is now strengthened due to the electron withdrawing effect of the benzene ring. You could add that. Okay, you could mention that. Same thing. It is strengthened due to the electron withdrawing effect of the benzene ring. Now we have this compound over here, which is chloride, and it is an ester essentially. Okay, so what are we doing to the ester? Firstly, we are hydrolyzing it with alkali. Okay, what did they ask? Give the systemic name for T. Interesting. So this is an ester. So the alcohol component has 2 carbons, so that is ethanol, and the acid part has 1, 2, 3 components, that is propanoic acid. So ethyl propanoate, however, um, it has, you know, this is, what is this compound? I agree that this is propanoic acid, carbon 1, 2, 3, but on carbon 3 it has a chlorine group. So what is the acid actually? It is 3-chloropropanoic acid and the 3-chloro. And on the other hand, we have ethanol. So what is this actually? It is ethyl propanoate, but it is ethyl 3-chloropropanoate. So that is the answer. This is actually ethyl 3-chloropropanoate. Okay, so if you have any side chains, just add it with the acid's name after. Ethyl for ethanol and 3-chloropropanoate for 3-chloropropanoic acid. Pretty straightforward. So if I break it down, what do I get? The alcohol part is simply this one over here, just ethanol. I think we had ethanol up there as well, somewhere over here. Same ethanol. And now what? When we break it down, what's gonna happen? So this is a thing that I don't get. How is this possible? In the acidic hydrolysis of amines, they did not write NH2 plus, although the lone pair is available. It's a Bronsted base. They should have written that. I don't get it. But in the alkaline hydrolysis, they draw the salt. That's so unfair. So I draw the chlorine over here, up, down, like this. And yeah, we get O minus Na plus. This is the compound. They just wrote ONA though, because you do get 3-chloropropanoic acid, but since this is alkaline hydrolysis, the excess alkali reacts with the acid to form a salt. Okay, that's the basis. Next, we convert it in step 1 to a nitrile. We convert the halogenoalkane, the chlorine, to a nitrile by using KCN in ethanol, right? Ethanolic KCN, and heat under reflux. And for Y, when you add excess HCl, when you hydrolyze it, you do get ethanol again. And on the left hand side, this is acidic hydrolysis. So we are gonna end up with the carboxylic acid on the right hand side, clearly on carbon 1, carbon 2, carbon 3 over there. But you know that nitriles have two roots. I always tell this to my students that nitriles have two roots. For a nitrile CN, you can do two things. You can either reduce it using LiLH4 or hydrogen plus nickel to get amine, or you can do hydrolysis acidic or alkaline H plus aqueous and heat, where you end up with a carboxylic acid. So similarly, since we are heating it with the next acid, we are going to get a carboxylic acid. Okay, so you end up with this. You can write it like this, or you could go for the skeletal formula. So carbon 1, 2, 3, 4, 1, 2, 3, 4. There you go. It's the carboxy acid. So see if you guys get it. So what is the reagent for step 1? It is ethanolic KCN and heat under reflux. And for step 2, what's happening when we find out the Z? What is this? C6H13NO2. The hell is that? Oh, okay. So this might be the other route, because this is hydrolysis. So clearly they might be testing the reduction route. So let's just try, then I'll match. Because I get a nitrogen, and yeah, nitrogen is still conserved. So let's see. O again, like this. And after reduction over here, what do we get? CH2 NH2. But yeah, if you write down the skeletal formula, you can't write CH2. CH2 will just be another simple vertex, right? Sorry about the delay. It's just some lag. So CH2 is just on the vertex, and over here we are gonna get NH2. So let's just match the number of carbons. It's CO, O, CH2, CH3, and over here this compound. So this is carbon 1. So for carbon 2 CH2, carbon 3 CH2, carbon 4 again CH2, and we get an extra NH2. So we have one nitrogen, that's fine. We have two oxygen, O2, that's fine. For carbons, we have 1, 2, 3, 4, 5, 6, that is C6. And for hydrogen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Perfect. So whenever you see nitriles, Cambridge must test you. Okay, like how do you form a nitrile? Using alcoholic KCN plus heat. And what are the two routes? Hydrolysis to form carboxylic acid and reduction to form an amine. This is a must, and the condition for step 2 is either LiLH4, which is preferred, or you could go for hydrogen plus nickel catalyst. Okay, perfect question by Cambridge, honestly. Draw the structures. We have drawn them, and state the reagents. You'll see that it will match whatever I've said. NaCN, KCN. So guys, if you need all of these, access to all the notes for all the topics in organic chemistry, as well as all my solved question papers from 2016 to 2023 and even older ones, please do consider supporting me on Patreon. It's just $5 for the tier where you get access to notes and question papers, and $15 for the tier where you get access to much more, including Patreon shoutouts, as well as video calls with me where you can get access to all these notes and tricks for solving question papers. So please consider supporting me there. In ethanol, and we need heat, they mentioned this in a bracket. And for step 2, the options are hydrogen plus nickel, or you could go for hydrogen plus platinum, and they said allow LiAlH4. So it seems like they are deviating towards this more now. Okay, interesting. Let's move on to the next one. Oh, okay. This is a bit more critical though. I feel like I've overlooked this. Okay, because if you use LiLH4, there's an issue. LiLH4 also reduces the carboxylic acid, or ester, I mean. Yeah, uh, esters are also reduced by LiLH4. Okay, so that is an issue. LiLH4 can reduce carboxylic acids to primary alcohols, amides to amines, then nitriles to amines, aldehydes and ketones to primary and secondary alcohols, as well as esters. That is why they said allow LiH4, but this is actually wrong. In fact, in this question, it would have been ideal if you chose hydrogen plus nickel. Interesting. Very good question. Now, the proton spectrum of compound T is shown, C5H9O2 and CdCl3. Okay, fine. So let's draw compound T. It's going to be easier for all of us. I know that you guys have problems in NMR. So notes for NMR are also included in the support for Patreon, right? Okay, so compound T. I'm going to draw compound T here. So I have CH3 at the end. Then I have CH2 over here. Then I have this oxygen followed by this carbon with this double bonded O, another CH2 followed by another CH2 followed by a chlorine atom over here. So I'm going to color code them. So this is it a proton NMR? Yeah, proton NMR. So this is a unique environment. I'm going to call this environment A. This is also unique because it's just next to oxygen. Now this is also unique because it's next to a C double bonded O. And finally, this CH2 is also unique because it's next to a chlorine atom. These are all unique environments. So we should be getting 4 peaks in total. 1, 2, 3, 4. That's perfect. As well as 1 peak for CdCl3, our reference, yeah? Reference peak. We are comparing all of these peaks to CdCl3. So now let's just match the environments. Okay, so check this. A should be, right? A should be triplet. Why? Because it is next to a carbon which has 2 hydrogen atoms. Similarly, B should be quartet because it's next to a carbon which has 3 hydrogen atoms. So 3 plus 1 is 4, quartet. What about C? C should be a C should honestly be a triplet because it is next to a carbon with 2 hydrogen atoms, and D should also be a triplet. Sorry about the color coding. Wait up, let me fix this. D should be a triplet because it is next to CH2, the pink one, which has two hydrogen atoms. Yeah. So that's the basic thing that you guys need to understand first. Like if your adjacent carbon atoms have 3 hydrogen atoms, you are going to be a quartet. 3 plus 1 is 4. If it has 2, you're going to be 2 plus 1 triplet. And if it has 1, you're going to be a doublet, because 1 plus 2 is in fact, 1 plus 1 is 2. So it's always n plus 1. Okay, number of hydrogen atoms plus 1 gives you the pattern. Triplet, yeah. Okay, so let's match with the diagram. We should have 3 triplets and 1 quartet. So 3 triplets. Okay, this is a triplet, this is also a triplet, and 1 quartet over here. Fine. So clearly I have identified one answer already. The quartet at 3.9, the quartet at 3.9, it is clearly the one that is next to the oxygen. So according to my diagram over here, right, according to my diagram over here, it is this one is B, or the CH2 that is next to an oxygen, that is 3.9. Fine. Next, what about the other ones? All of those are triplets, but I actually need to see the values to actually so let's match this. An alkyl next to electronegative atom like oxygen, it is within 3.2 to 4, so perfect. That is next to. Next, as you can see, another one, we already have another one, the blue one. See, environment D, that is also next to an electronegative atom, chlorine, which is also between 3.2 to 4. So clearly this one is this one over here, this one, right? This is my environment D, and it should be CH2Cl, clearly. Now for the other ones, we have the pink one, which is a CH2 next to CO, next to CO, CH2 next to CO, which is within 2.2 to 3, 2.2 to 3, which matches the range for 2.8. So clearly, yeah, this is my environment C, which is the CH2 next to CO, C double bonded O. And finally, the last one, CH3, the typical alkane, it is from 0.9 to 1.7, which is fine, fits the range. This is just my CH3, just my alkane. So I have my answers now. Now, the typical questions that we're going to face are, why is CdCl3 used? Okay, as a solvent instead of CHCl3. So, thing is, remember, CdCl3 is a solvent. Why? Because it is not NMR active, because it is made up of deuterium, which has a even number of nucleons. As a result, it is NMR inactive, and it is used as a solvent. But on the other hand, what is used as our solvent? Typically we use tetramethylsilane, TMS, okay, because it is very shielded, we could say. Yeah. So why is it used? Because the solvent D or CdCl3 does not give a single peak. Sorry, I read it wrong. They wrote signal. Does not give a signal or any peak or any absorption. Alright, next. Complete table 8.2 for the proton spectrum of T. So chemical shift. So I've already told you guys that the splitting pattern is triplet for all of them except the one at 3.9. That's a quartet. So that is a quartet, the one on the left hand side. I'm gonna color code them. Quartet, and these are all triplets. Okay, this is also a triplet. This is also a triplet. That is the splitting pattern. Now, how many hydrogen atoms are responsible for them? Sorry, I forgot to mention this. So yeah, clearly 2 for this one, then also 2 for this one, I'm counting the hydrogens in that particular environment, not my adjacent environment, okay? Then CH2CO, also 2 here, and for this it's 3. So from above downwards it's 3, 2, 2, 2. 3, 2, 2, 2. Okay. You guys got it, right? Hopefully. Like suppose I'm talking about environment D, which is a, suppose I'm talking about environment B, which is a quartet. Although it has an adjacent carbon with 3 hydrogens, in its own environment, the blue circle, the orange circle, sorry, it has 2 hydrogen atoms. Okay. Sorry, it's lagging a bit. So it's going to be 3, 2, 2, 2. Yeah. So much lag. So it's okay. So we know the number is going to be 3, 2, 2, 2. And I talked about the environment of the protons. The first one is simply a CH3 or an alkane. I'm just following the box over here, alkane. And then the next one, the pink one is next to a C double bonded O. The next one is alkyl, alkyl next to C double bonded O, or you could just state that it is, a CH2CO. That's also fine. And for 3.7, we know that it is next to the Cl electronegative atom. It is basically a CH2Cl, or you could say that it's alkyl next to electronegative atom. Alkyl next to electronegative atom. Same goes for the one below. You could just say that it's CH2O, or as usual, alkyl next to electronegative atom. Okay, just go for the easy one. Simply CH3, CH2CO, CH2Cl, CH2O. Explain the splitting pattern at 3.9. Why is it a quartet? The one at 3.9. I just taught you because look at this. The adjacent carbon atom, the one over here, has 3 hydrogens. So 3 plus 1 is 4 quartet. Okay, so let's do that. At del 3.9, we have 3 H atoms on adjacent or neighboring or adjacent carbon, or you could say that it's next to a CH3. If you're next to a CH3, you're going to turn into a quartet. Okay, so finally we move on to question 9. Standard cell potential. Let's end this, all right, on a good note. Electrochem, it is the potential difference, or the voltage between the two half cells, or two electrodes, two half cells or two electrodes in a cell under standard conditions. In a cell under standard conditions. Fine. An electrochemical cell is set up to measure E cell using Fe3 plus 2 plus and a chlorine half cell. So chlorine is a gas half cell, right? So let's do this. Let's draw it. So here you go. One vessel over here and another vessel over here. Free marks, yeah. Include all necessary substances. It is not necessary to state conditions used. Okay. So for the chlorine electrode, it has to be platinum, right? I taught you in previous videos that platinum is going to be the electrode of choice for electrodes which have, metal ion in 2 different oxidation states or a gas half cell. It is always going to be platinum. And we don't have a battery, but rather than that we have a voltmeter on top, like this. Okay, fine. What else? There you go. Next, I'm going to make this the half cell, gas half cell. So we need chlorine gas entering this vessel, and obviously this one over here is platinum, platinum black, also platinum solid over here. And what about the electrolyte itself? For this electrolyte, we need chloride ions aqueous 1 mole per dm cube. They said that it's not necessary to mention the conditions, but we had to mention 1 mole per dm cube. And this solution is Fe2 plus aqueous, also Fe3 plus aqueous. Okay, and yeah, that is 1 mole per dm cube of each. And what do we need to finish things off? We need a salt bridge. So there you go, that is your salt bridge. It completes the circuit, and this is your voltmeter. So 2 electrodes, 2 electrolytes, 2 vessels, 1 salt bridge, and 1 voltmeter to end it all. Okay, and you to label chloride ions, iron 2 plus, iron 3 plus ions, and the platinum electrode on both sides, and the entry for chlorine gas. All right. Okay, the cell reaction for the electrochemical cell in B is shown. Calculate del G. So yeah, this is the new addition to the syllabus starting from 2022 onwards. So what is the formula? It is del G is equal to minus NF E cell standard, where N is the number of electrons transferred. Clearly, the number of electrons transferred is 2. It went from 0 to minus 1, but 2 of them, so 2 times 1 electron was transferred. Okay, so N should be 2. So let's just find out del G. So we have a minus sign. N should be 2 because 2 electrons were transferred, and the value of F is given over here. It is actually 96,500, which you should have memorized, honestly. 96,500. And the E cell for this equation is plus 0.59. So 0.59 times 96,500 times minus 2 gives you a value of minus 113870. So this is in joules, by the way. Okay, this is in joules. The answer that you will get is in joules. Now you have to convert it to kilojoules. So if you divide by 1000, you're gonna get minus 113.87 kilojoule per mole, which is rounded off to minus 114 kilojoule per mole. Okay, so remember to convert this to kilojoules. That's the tricky part over here. Okay, there's a chance that you might miss this. Why is that? Because it's all in SI units, right? This is in coulombs per mole. And yeah, so you know that voltage equals to work done per unit charge. So if you multiply it, joules per coulomb into coulomb per mole, we get rid of coulomb, we end up with joules per mole. That's the logic. So we need to convert to kilojoule per mole. Another experiment is set up using the same electrochemical cell, but in this experiment, the Fe2 plus concentration is 0.15 mole per dm cube. So we are not maintaining standard conditions of 1 mole per dm cube. All other concentrations remain at standard value. So use the Nernst equation to calculate the electric potential for Fe3 plus Fe2 plus half cell. Okay, so according to the Nernst equation, the new electrode potential will be equal to the standard one, which is plus 0.77 plus 0.059 divided by Z. What is the electron transferred over here in the reduction? Only 1 electron, right? So it's just plus 0.059 by 1 times log oxidized species. So what is the oxidized species? It is Fe3 plus. So that's simply going to remain at 1. However, The reduced species Fe2 plus, this is Fe3 plus. The oxidized species will remain at 1, but the reduced species turns to 0.15. So let's solve this. Log 1 by 0.15 times 0.059 plus 0.77. That gives you a value of plus 0.819 or 82 volts to 2 decimal places, plus 0.82 volts. Use the answer to find out the new E cell for this chemical cell. Okay, so let's try to find it out. So we know that in this equation over here, yep, what happened actually? Who is being reduced? Chlorine is reduced and iron is oxidized in this equation to get plus 0.59. So what is the actual value for iron? It's plus 0.77. Okay, so basically, according to the previous equation, reduction potential of chloride minus the reduction potential of iron or plus the oxidation potential of iron is equal to plus 0.59. Okay, so let's do that. The reduction potential of the chloride half cell, Cl2 to Cl minus, minus the reduction potential of the iron half cell, which is plus 0.77, is equal to the value of E cell, which is plus 0.59. Plus 0.59. So what is the reduction potential of the chlorine half cell? Is actually equal to 0.59 plus 0.77 plus 0.59 plus 0.77, which is actually 1.36 plus 1.36. Now we can find out the new E cell. How? So the new E cell is equal to the reduction potential of chlorine, which is plus 1.36, minus the new reduction potential of iron, which is minus 0.82 plus 0.82. So 1.36 minus 0.82, which is giving me answer of plus 0.54. So plus 0.54 volts is my final answer. So do you get it? This was actually a bit tricky. This part was easy using the Nernst equation. I just input the values of the standard conditions, Fe3 plus, and the new concentration of Fe2 plus, reduced it down below. So we have the new E electrode of iron. So I used the value of the original E cell under standard conditions and the value of the iron half cell electrode potential to find out the reduction potential of the chlorine half cell. Okay, so I found that using this reduction potential higher one, chlorine, because it was getting reduced clearly according to my equation over here. The one that gets reduced, that reduction potential will always come first. Okay, so reduction potential of chlorine minus reduction potential of iron, which is under standard conditions 0.77. I found out the standard electrode potential of chlorine, reduction potential. Then I found out the new E cell by doing reduction potential of chlorine under standard conditions minus the new electrode potential of iron, which is plus 0.82, to get a final value of plus 0.54. Okay, so really huge paper. That's why I hate doing chemistry P4, but I will try to solve paper 4.1 before your exam on the 27th of October. A lot of you have been requesting this paper and the other one. I will be doing that. But overall, yeah, my comment is difficult paper. Quite difficult as usual. It is testing your skill. Maybe not as hard as fewer older questions that I faced, but honestly, it was overall like maybe I'd say that 70 to 80 marks were pretty easy, but the atypical questions were brand new, completely new, things that I have never seen before. So that made this question a bit more complicated. Maybe it was harder to get a star, but getting an A was relatively easy in this paper. Okay, so quick shout out to my highest tier patrons for the month, Dewa, Luna, sorry, and Sean. And yeah, guys, if you want to be featured on the end screen, please do consider supporting me on Patreon on the highest tier, where you get access to my notes for physics and chemistry, as well as solve question papers from math, physics, chem, and bio, as well as video chats with me once or twice a month. Also, I will link the paper for May June 2023, variant 41 or 43, when I solve that up here, and the variant for February March 2023, paper 42, down here. And yeah, the playlist for chemistry P4 up here. So hit the subscribe button. See you guys. Bye bye.